Someone walks into what appears to be an ordinary American residential bathroom. The toilet is on the right. A vanity with a sink is on the left. At the back is a bathtub with a shower, enclosed by a curtain. The floor may be ceramic tile, vinyl, or a material designed to look like wood. Everything seems perfectly normal, until someone pours a bucket of water directly onto the center of the floor. The water spreads in every direction. Some flows beneath the vanity. Some reaches the base of the toilet. A small stream runs toward the door, but none of it flows toward a drain because there is no general floor drain. The homeowner has to grab towels, rags, or a wet vacuum before the water finds its way through the joints, reaches the edges of the walls, or penetrates some vulnerable point. Now imagine the same scene in many Brazilian bathrooms. The bucket is poured out. The water spreads there too, but the floor has an almost invisible slope. With a few passes of a floor squeegee, the water is directed toward a small grate. It disappears down the drain and continues through the plumbing. The comparison raises an unavoidable question. Why would one of the rooms most closely associated with water be built without a drain in the floor? The answer seems simple. Perhaps Americans simply don't clean their bathrooms by pouring water across the floor. That statement describes a common practice, but it doesn't explain how the practice began. In fact, keeping water off the floor is also a consequence of how the room was built. Another popular explanation blames wood frame construction, and wood does play an important role. A large share of American homes use light frame construction, wood joists, and wood-based panels beneath the finish materials. But that still doesn't solve the mystery. American homes built with concrete can also have bathrooms without general floor drains. At the same time, it's perfectly possible to build a waterproofed, drained bathroom over a wood structure. Perhaps the answer lies in the bathtub. For many years, the bathtub and shower combination dominated residential bathrooms in the United States, but many modern designs have eliminated the tub and installed separate showers. Even then, a general drain in the bathroom floor is still often absent. That leaves the cost explanation. Eliminating a drain means using less piping, fewer connections, and less labor. That reduces costs, but the drain is only the visible part of a much larger construction difference. To solve the case, it isn't enough to ask where the drain is. We need to determine which part of the bathroom was actually designed to get wet. In many Brazilian bathrooms, the shower enclosure defines an obvious wet area. That's where the shower continuously releases water. Even so, the rest of the floor is usually finished with moisture-resistant materials, and many designs include a second drain outside the shower enclosure. Even when that additional drain is absent, it remains relatively common to build the room with the expectation that some water may reach the floor during cleaning or everyday use. In American residential construction, the boundary is usually more rigid. The shower or bathtub receives the waterproofing and drainage it needs. Outside that perimeter, the floor may be treated almost like the floor of a hallway, bedroom, or any other room meant to remain dry. It needs to withstand normal humidity, splashes, and minor accidents, but not necessarily buckets of water spread across it repeatedly. This is the first decisive clue. The drain wasn't simply forgotten. It was placed precisely where the water was supposed to remain. To understand how this philosophy gained traction, we need to go back to the rise of the modern residential bathroom in the United States. As water and sewer networks expanded and indoor plumbing became more common, the bathtub took on a central role. Over time, the shower was incorporated into the same fixture. The bathtub solves several problems at once. Its body acts as a large waterproof container. Water comes from the shower head, hits the person, and falls into this container. A curtain or door limits splashing. The tub has its own drain connected to the sewer system, and usually an overflow designed to reduce the risk of water spilling over the edge. In this system, the bathroom floor doesn't need to direct water anywhere. Its only job is to support foot traffic, furniture, and fixtures. If everything works as intended, it receives little more than drops from wet feet, or small splashes that are quickly wiped away. Compare that with a very common Brazilian shower enclosure. The shower doesn't discharge water into a raised, factory-made container. It discharges directly onto part of the floor itself. That area receives waterproofing, tile, and a slope toward the drain. One system places a container on top of the floor. The other turns part of the floor itself into the container. It seems like a small difference, but it changes how the entire room is built. A bathroom designed to receive water across the floor requires far more than cutting a hole and installing a grate. Beneath your feet is a sequence of layers that must work together. First comes the structure, which may be a concrete slab or another type of base. Above it is usually a screed or mortar bed, a layer that levels the surface and makes it possible to create the slope. Waterproofing, the drain, and the connection to the waste pipe are installed in designated locations. Above those come the setting mortar, tile, and grout joints. The slope is essential. Although the floor appears level, it has a deliberate pitch. The difference in height may be subtle, but it must be sufficient for gravity to carry the water toward the drainage point. Imagine a table that appears perfectly flat. If one side is raised by a fraction of an inch, a small ball placed on the surface will begin to roll. Water behaves in much the same way, although minor irregularities can divert it and create puddles. That's why installing a drain in a completely flat floor doesn't guarantee that the room can be washed down. Water may remain in the corners, collect near the door, or become trapped behind the toilet. A drainable bathroom has to be designed in 3 dimensions. Every relevant point on the floor must direct water toward the correct destination. The water must also be prevented from following an invisible path. Ceramic tile helps protect the surface, but it can't replace a waterproofing system on its own. Water can pass through flaws in the grout, transitions between materials, pipe penetrations, or extremely small cracks. If the underlying layers aren't properly prepared, moisture may reach the structure, the neighboring wall, or the ceiling below. Even the transition between the floor and the wall demands attention. Water doesn't understand the visual division between 2 finishes. It searches for joints, gaps, and low points. A reliable system must account for drains, corners, thresholds, and every penetration made for pipes or fixtures. This is where American light frame construction becomes important. Many homes in the United States have wood joists supporting the floor. Structural panels, generally known as the subfloor, are fastened over these joists. This subfloor forms the platform on which the preparation layers and finished flooring will be installed. The subfloor isn't simply the floor we see. It's the structural surface hidden beneath the finish. In a 2-story house, directly below it may be joists, insulation, electrical wiring, plumbing, and finally the ceiling of the lower floor. Wood performs perfectly well in millions of buildings and can last for many decades when it's properly designed and protected. By definition, it isn't incompatible with bathrooms. The problem begins when water repeatedly reaches parts that were meant to remain dry. A persistent leak can reach the panel joints. Moisture can cause swelling, warping, stains, odors, damaged finishes, and, over time, decay in structural components. Water can also travel down through plumbing penetrations and appear on the ceiling below, far from where the problem began. Instead of heavily waterproofing the entire bathroom, the traditional solution was to concentrate protection within a small area. The bathtub, shower pan, or shower enclosure receives the components capable of handling constant water exposure. The rest remains dry. This strategy doesn't make light frame construction inferior. It simply assigns functions differently. The system relies less on draining the entire room and more on containing water where it's used. Now comes an important twist. When someone enters an American bathroom finished with ceramic tile, they may assume that the entire floor is waterproof. After all, the surface looks similar to that of a Brazilian bathroom. But appearance and performance aren't the same thing. Porcelain and ceramic tile resist water extremely well. That doesn't mean the entire assembly beneath them was designed to function as a basin. Grout may allow moisture to pass through gradually. The floor edges may not have a continuous membrane extending up the walls. The doorway threshold may have no barrier at all. Penetrations and transitions may have been detailed only to withstand occasional splashes. Inside a modern shower, the situation is different. Beneath the finish may be a waterproof membrane carefully integrated with the drain. Other systems use a preformed base, a factory-made shower pan, or a specialized assembly of materials that creates a watertight area. The shower walls also receive treatment appropriate for frequent water exposure. Outside that zone, the same level of protection may simply not exist. So pouring water over the entire floor of a bathroom designed to remain dry isn't merely a different cleaning method. It can mean introducing water onto an assembly that was never prepared to receive it. The presence of drywall on the walls makes this boundary even more important. Different boards and systems are designed for different conditions, but a wall outside the shower generally isn't treated like the inside of a swimming pool. Water pooling along its base can reach baseboards, joints, screws, and internal layers. Could a general floor drain solve all of this? Not by itself. Adding one correctly would require modifying the entire floor. The drain would need piping, a connection to the sanitary system, space between structural elements, and a position that allows the proper slope to be formed. The floor would need to direct water toward it, and every surface exposed to water would require compatible waterproofing. In a concrete slab, a builder can accommodate pipes and create different screed thicknesses. In a floor built from wood joists, space is also available, but everything must be coordinated. A pipe can't simply pass through any part of a structural joist. Holes, notches, and rerouting must respect the design and the limitations of those components. The slope can also interfere with doors, hallway elevations, the toilet base, and cabinetry. If the drain is in the center, several planes of the floor must converge toward it. Large format tiles can make these changes in plane harder to execute. A linear drain simplifies some geometries, but it adds cost and requires careful installation. In addition, every drain connected to the sewer must prevent gases from flowing back into the room. This function is usually performed by a trap or water seal. A small amount of water remains in part of the pipe, creating a barrier between the bathroom and the sewer system. It's like a door made of water. Liquid from the bathroom can pass through it, but air rising from the sewer finds its path blocked. When a drain is used regularly, this barrier is renewed. But a general floor drain installed in a bathroom that almost never gets wet may go unused for months. Gradually, the water retained in the trap can evaporate. Once the water seal disappears, odors and gases can enter the room. Depending on the application and local requirements, devices and other solutions can be used to maintain or restore this water seal. But this confirms an important point. Every new drain also adds a component that must continue working for years. It removes water, but it also adds piping, maintenance, structural coordination, and new potential points of failure. If the design assumes that the floor will never be flooded, there may not be enough reason to accept all that complexity. This is where architecture and behavior begin to reinforce one another. In many Brazilian homes, washing the bathroom with water became common because the room allows it. The floor is tiled, drainage is available, and a squeegee directs the water. Residents organize their cleaning routine around the features built into the room. In the United States, cleaning is more likely to involve a vacuum, mop, cloth, directly applied cleaning products, and controlled amounts of water. Surfaces are cleaned individually. The floor receives enough moisture to remove dirt, but not a sheet of water searching for a drain. That doesn't mean one method is automatically more hygienic than the other. Effectiveness depends on the products, frequency, execution, and surfaces involved. The relevant difference is that each habit has adapted to the available space. Brazilians can pour water across the floor because the bathroom was often designed to drain it. Americans avoid doing so because the bathroom was generally designed to remain dry. After decades, the consequence begins to look like the cause. We say there's no drain because people don't pour water on the floor. But they also don't pour water on the floor because there's no drain, slope, or comprehensive waterproofing. So what happens when an American home removes the bathtub and installs a modern shower? We enter the world of walk-in showers. A person steps directly into a tiled bathing area. There may be a small curb, a glass door, or an open entrance. The floor is sloped and directs water toward a central or linear drain. At this point, the system begins to resemble many Brazilian shower enclosures. The shower base itself functions as a drainage surface. Beneath it is a pan, membrane, or waterproof assembly connected to the drain. Even so, the slope usually remains confined to the shower area. The rest of the bathroom stays relatively level. A partition, curb, or the geometry of the base prevents water from spreading outward. In curbless designs, this separation becomes more delicate. The transition must provide accessibility without losing the ability to contain water. The shower head's position, the direction of the spray, the length of the sloped area, and the location of the drain all become essential. There's also another concept, the wet room. In a wet room, a much larger portion of the bathroom, or even nearly the entire space, is treated as a wet area. The floor receives comprehensive waterproofing, slope, and drainage. Depending on the design, the shower may not have a fully enclosed stall. And then something revealing happens. When an American bathroom is designed to receive water across a larger area, the floor drain reappears. This shows that its absence was never an inexplicable cultural rule or a technical prohibition. It's the logical result of a bathroom divided between a small wet zone and a large dry zone. When that division changes, the plumbing changes too. The United States has many spaces with floor drains. They can be found in commercial restrooms, shared facilities, locker rooms, areas near swimming pools, laundry rooms, basements, mechanical rooms, and places vulnerable to leaks. Accessible showers and institutional designs may also use continuous drained surfaces. Building and plumbing codes vary by state, city, building type, and use of the space. There is no single national rule capable of describing every American bathroom. One jurisdiction may require drainage for a particular application, while another doesn't. A custom residential design may also include a drain, even when it isn't mandatory. Likewise, not every Brazilian bathroom has a general floor drain. Some have only the drain inside the shower enclosure. Others use bathtubs, prefabricated bases, or systems in which the area outside the shower must remain dry. Renovations and contemporary apartments may adopt different combinations. We're comparing construction trends, not universal laws. The best way to visualize the difference is to imagine cutting through both floors. In a Brazilian bathroom designed to handle water, we find the structure. Above it are the leveling and waterproofing layers. Then comes a sloped screed, the setting material, and the tile. Somewhere within this assembly, the drain passes through the layers and connects to the waste pipe. Each component helps transform the floor into a surface capable of receiving and directing water. Now we cut through a typical American bathroom. We find joists or another structural base. Above them is the subfloor. Next come the preparation layers and the finished flooring. But inside the bathtub or shower, a second specialized system appears. A container, base, or waterproof membrane, along with a slope and its own drain. Visually, both rooms may contain ceramic tile, a toilet, a sink, and a shower. Beneath the surface, they manage water in different ways. The difference we see in that small metal grate begins several inches beneath our feet. Which system is better? There's no absolute winner. A bathroom with a waterproofed, sloped, and drained floor offers considerable flexibility for cleaning with water. If a minor leak occurs at a visible connection, some of the water may reach the drain, provided the slope and the position of obstacles direct it that way. But this protection depends on proper workmanship. An incorrect slope creates puddles. Defective waterproofing causes leaks. A poorly connected drain can produce water damage or odors. The American model simplifies the areas intended to remain dry. The most intensive waterproofing is concentrated where exposure is predictable. This works well with bathtubs, shower pans, and light frame construction. But when water escapes that zone, the damage can be greater precisely because the outer layers may not be designed to handle it. A wet room allows greater freedom of use and can improve accessibility, but it requires more materials, detailing, waterproofing, and slope control. The larger the wet area, the more transitions, corners, and penetrations must remain watertight. The best solution depends on the structure, climate, budget, local codes, and, above all, how residents intend to use and clean the space. An effective design doesn't simply copy another country's appearance. It brings materials, plumbing, and behavior together. So we return to the two bathrooms from the beginning. In the Brazilian bathroom, the drain remains visible. The slope is almost imperceptible, but it's there, guiding every stream of water. In the American bathroom, the floor still has no drainage point. The water must remain inside the bathtub or shower, exactly where the waterproofing and dedicated drain are located. Now, the absence no longer looks like an oversight. One room was historically built to tolerate water spreading across a larger portion of the floor. The other was built to trap it within a designated area. That's why American bathrooms generally don't need a general floor drain. The design attempts to keep water from ever reaching that floor. It isn't merely a difference in cleaning habits. It's a choice involving the structure, subfloor, waterproofing, piping, finish materials, and decades of architectural tradition. And if you enjoy discovering how seemingly small choices reveal enormous differences between homes around the world, follow the channel. Because the drain that appears to be missing reveals something much bigger. One country designed the bathroom to drain water. The other designed it to keep water from ever reaching the floor.